2B1Q 2B1Q, 2 binary, 1 quaternary, is a multilevel line coding technique used to transmit digital data over copper wires. It is a form of pulse amplitude modulation, PAM4, that encodes 2 bits of binary information into a single quaternary, 4-level, symbol. How 2B1Q works in a standard binary system: each signal change, baud, represents 1 bit, either 0 or 1. 2B1Q doubles this efficiency by grouping bits into pairs, called dibits, and mapping them to one of 4 specific voltage levels. The standard mapping, using gray coding to minimize errors, is typically, dibit, 2 bits, quaternary symbol voltage level, typical, 10 plus 3 plus 2.5 V 11 plus 1 plus 0.833 V 01 minus 1 minus 0.833 V 00 minus 3 minus 2.5 V. Note, by using gray coding, adjacent voltage levels only differ by a single bit. If noise causes the receiver to misread a +3 as a +1, only 1 bit is wrong instead of 2. Why 2B1Q is used? The primary reason for using 2B1Q is bandwidth conservation. Reduced baud rate: since each symbol carries 2 bits, the symbol rate, baud rate, is exactly half the bit rate. For example, to transmit at 160 kbps, the line only needs to pulse at 80 k baud. Lower frequency requirement: lower baud rates require less frequency bandwidth. Copper telephone lines have high attenuation at high frequencies. By keeping the signal slow and low frequency, the data can travel much further distances, up to 5.5 kilometers or 18,000 feet, without a repeater. Power efficiency: it uses power more efficiently than simpler codes like Manchester or AMI, alternate mark inversion, for the same data throughput. Where 2B1Q is used: while modern residential broadband, like VDSL2, has moved to the more complex DMT, discrete multitone, modulation, 2B1Q remains a foundational technology in specific telecom sectors. Integrated Services Digital Network, ISDN. 2B1Q is the standard line code for the ISDN BRI, Basic Rate Interface, U interface in North America. 11. It allows a single copper pair to carry 264 kbps B channels, voice/data, and 116 kbps D channel, signaling. HDSL, High Bitrate Digital Subscriber Line. Early versions of HDSL used 2B1Q to provide T1/E1 speeds, 1.5 to 2.0 Mbps, over copper loops. It was the workhorse for connecting business offices to the phone company before fiber optics became common. IDSL, ISDN Digital Subscriber Line. IDSL is a hybrid technology that uses ISDN hardware and 2B1Q coding but connects to a data network, DSLAM, rather than a voice switch. Legacy MSAN connections. In an MSAN, multi-service access node, 2B1Q is still supported on specific line cards to maintain service for legacy ISDN business customers who haven't yet migrated to VoIP. Summary of pros and cons. Advantages: disadvantages. Halves the required not DC balanced, long strings of zeros can cause bandwidth/baud rate. Baseline wander, DC offset. Extended reach over long copper receiver complexity: the receiver must distinguish loops between 4 distinct voltage levels. Reliable and well standardized, lacks self-synchronization for certain bit patterns. ANSI T 1.601. Analysis of pros and cons for 2B1Q. The 2B1Q, 2 binary, 1 quaternary, line coding scheme was a breakthrough for digital communications over existing copper wires. Its primary value lies in its ability to transmit more data using less effort, bandwidth, but this efficiency comes with a trade-off in receiver complexity and synchronization. Pros of 2B1Q: bandwidth efficiency, high throughput. By encoding 2 bits into a single quaternary, 4-level, symbol, it effectively halves the baud rate required for a given bit rate. For example, a 160 kbps stream only requires an 80 kHz symbol rate. Extended reach: longer distance lower frequencies travel further on copper wire because high frequency signals suffer from greater attenuation, signal loss. By lowering the required frequency, 2B1Q allows services like ISDN and HDSL to reach customers up to 5.5 kilometers away without needing expensive repeaters. Cross-stalk reduction: since the signal operates at lower frequencies, it generates less electromagnetic interference, next, near-end cross-stalk, for neighboring wires in a cable bundle compared to high-frequency binary schemes. No redundant signals: every possible 2-bit combination maps exactly to one of the 4 voltage levels. This means there is no wasted signal space, maximizing the use of the available voltage range. Established reliability: it is an extremely stable, standardized technology, ANSI T 1.601, that has been the global workhorse for business-grade ISDN and HDSL for decades. Cons of 2B1Q: receiver complexity: unlike binary systems that only need to distinguish between high and low, a 2B1Q receiver must accurately distinguish between 4 distinct voltage levels, example -2.5 V, -0.833 V, +0.833 V, and +2.5 V. This requires more precise analog-to-digital converters and sensitive circuitry. Reduced noise margin. Because there are 4 levels packed into the same voltage range, the gap between signal levels is smaller. This makes the system more sensitive to noise. A small spike that wouldn't affect a binary signal might cause a 2B1Q receiver to misinterpret a +1 level as a +3. Lack of self-synchronization. 2B1Q does not guarantee a voltage transition with every symbol. If a long string of identical bit pairs is sent, example 000000, the signal remains at a constant voltage, -3V. Without transitions, the receiver's clock can drift, leading to a loss of synchronization. Solution: to fix this, systems using 2B1Q often employ a scrambler to randomize the data and ensure enough transitions occur to keep the clocks in sync. DC component/baseline wander. 2B1Q is not inherently DC balanced. Certain data patterns can cause a buildup of direct current, DC, on the line. This can cause baseline wander, where the average voltage level shifts, making it even harder for the receiver to correctly identify the 4 levels. Power consumption. Generating and maintaining 4 distinct, precise voltage levels typically requires more power than simpler 2-level, binary, or 3-level, AMI, line codes. Summary table feature 2B1Q traditional binary, NRZ, bits per symbol to 1 bandwidth REQ low, half the bitrate, high, equal to bitrate, reach excellent, long distance, limited noise sensitivity higher lower implementation complex simple. Why 2B1Q is not spectrum friendly? When engineers say that 2B1Q is not spectrum friendly, they are usually referring to its impact on other services within the same cable bundle. While 2B1Q is very efficient at using the bandwidth of a single wire, it is a noisy neighbor to other wires. The lack of spectrum friendliness stems from 3 main technical areas. 1. High power spectral density, PSD. 2B1Q is a baseband signal, meaning its energy is concentrated at the lower end of the frequency spectrum. The problem: it puts a lot of power into a small frequency range. When many 2B1Q lines, like HDSL or ISDN, are packed together in a single thick telephone cable, the high energy from one wire leaks into the others through electromagnetic induction. The result: this causes significant cross-stock, specifically near-end cross-stock or next, which can degrade or completely crash more sensitive services like ADSL or VDSL running in the same bundle. 2. Presence of a DC component. As mentioned in previous sections, 2B1Q is not DC balanced. Low frequency noise. If a sequence of bits results in a constant voltage, like long strings of zeros, it creates a DC offset. 1. Spectrum waste. This energy at 0 Hz, DC, and very low frequencies cannot carry data through transformers or AC coupled equipment, yet it still generates heat and potential interference. Modern spectrum-friendly codes like 4B3T or DMT ensure the energy at 0 Hz is 0, a DC null. 3. Wide VS-shaped spectrum. Modern modulation schemes like DMT, used in ADSL/VDSL, are considered very spectrum-friendly because they are surgical. DMT can turn off specific frequencies that are known to interfere with amateur radio or other DSL lines. 2B1Q is a blunt instrument. Its power is spread across its entire operating range, up to 80 kHz or 240 kHz, in a fixed way. You cannot notch out a specific frequency with 2B1Q to protect a neighbor's service. Summary: the bad neighbor effect feature. Why its unfriendly energy high power in low frequencies causes heavy cross-stock into adjacent feature. Why its unfriendly concentration pairs cannot avoid specific frequencies used by other technologies, like AM no-notching radio. Wastes power and causes baseline wander, which stresses DC bias electronic components. Why did we use it anyway? Despite being unfriendly, 2B1Q was chosen for ISDN and HDSL because, at the time, receiver simplicity and maximum reach were more important than coexisting with other high-speed services. It wasn't until the broadband explosion, ADSL, that spectral compatibility became a requirement for new technologies.